Hello and welcome. What did the quantum physicist say to get her kids out of bed in the morning? Up and at 'em! And speaking of physics, in 8.3 we're going to look at two applications of physics or engineering. The first is hydrostatic pressure and force, and the second is center of mass. So let's get started. So with hydrostatic pressure and force, if you've ever gone swimming and you've swum down to the bottom of the pool, swam down, you'll notice that the deeper you go underwater, the more pressure you feel. You mostly feel it in your ears. And the reason for that is because you have a taller and taller column of water that's pushing down on you. So what we're going to focus on here is the question, how much force acts on objects that are underwater? And we'll start by thinking about a thin plate that has area A and is horizontal underwater at a depth D. Let me draw a little picture of a thin plate. We'll just make it a little rectangular plate. And it's underwater at a depth D. Here's the top of the water. Not a perfect rectangular prism, but close enough. The depth there is D, and the area of this thin plate, we're told, is A. Now the volume of the water that's above this thin plate, that's pushing down on it, can be given by V equals A times D, right? Because you can take the area of the plate, multiply by that depth of the water, and it's just like finding the volume of a rectangular prism. Take the area, which is kind of like a cross section, multiply by the depth, that other dimension, and that gives you the volume of that water, that rectangular prism of water. And then we can go on and find the mass of the water, which would be given by the weight density rho. So here we have the weight density rho. This is something that we used in, the mass density rho. This is something that we used in section 6.4 when we were talking about the work involved in pumping liquid out of a tank. We used rho there to represent weight density as well. So we have mass density. I keep saying the wrong thing. So we have the mass is equal to the mass density, which will be something like kilograms per cubic meter, and then times the volume, which might be in cubic meters. And so there we would just get kilograms in that case of mass. But volume, we already said, was A times D. It's the area of the thin plate times the depth of water. So the force then we could get by using F equals ma, or in this case, A acceleration is g, the acceleration due to gravity. So we would take the mass that we just created a formula for, rho AD, multiply it by g, and shuffling around the letters a little bit, we can get the force acting on the plate is rho g AD. Now circling back to pressure, we mentioned that the deeper you go, the more pressure you feel. The more force per unit area, in other words. That's how pressure is defined. Well, if we start with that thought, pressure is force per unit of area, you can write P equals F over A to represent that, where F we just figured out a formula for. It's rho g AD. Notice that the A's can cancel, so area comes out of the picture altogether. It doesn't matter what your area is, because you're trying to think of a force per unit of area, so it doesn't matter how big your area is. And so we just get that pressure is the mass density times the acceleration due to gravity times the depth that you're at. Now, the mass density and acceleration due to gravity don't really change that much. I mean, they might change a little bit, but it's pretty negligible. So really, pressure is varying linearly with depth. The deeper you go, the more pressure you're going to feel in a linear way. Now, this also gives us, so it's one good thing to kind of notice that, it also gives us a way of breaking down our calculation for force. You can write force as pressure times area by solving this equation P equals F over A for F. Just multiply the A over and you've got F equals PA. So usually in our problems, what we'll do is we'll figure out what pressure is using the rho g d kind of formula, and then we'll figure out what the area is of our object underwater, and then we'll multiply those two things together to get the force that's acting on the object. So that's going to be the hydrostatic force. One thing I should mention is the word hydrostatic. So the hydro is referring to like the water, and then static referring to not moving. So this is where a situation where the water is not moving. Okay, so a few more notes, a few notes. One note is a piece of software, but the first note says that at any point of a given depth, the pressure applied in all directions is the same. So if you look at any given point, there's water all around that point. And so the pressure is being applied from all directions. You don't have to have your ear facing upward to feel that column of water pushing down on it. The pressure is applied equally in all directions at that depth, right? At that depth. The second thing we mentioned, which is that pressure varies linearly with depth. And then the third thing says that for water, we're going to use, just like we did in 6.4, a mass density rho of 1,000 kilograms per cubic meter if our units are metric units. And then if our units are British units, then we'll use rho g, which is a weight density, as 62.5 pounds per cubic foot. Again, I'll give those values to you on quizzes or tests. The last note is that we can use this concept of a thin flat plane to represent a surface. So we could be talking about the bottom of a pool, like we will in example 1, or even the side of a swimming pool, or the side of a trough, or the side of a dam. So these are examples of what this thin flat plate is representing. It's representing the side of an object. So example 1 says we have a swimming pool full of water that is 12 feet wide, 20 feet long, and 5 feet deep. Let's draw a picture of that pool. Here's the bottom of the pool. That's 12 feet wide, 20 feet long. And then this is 5 feet deep. So to figure out the, so what we're looking for is the force that's acting on the bottom of the pool. Hydrostatic force acting on the bottom of the pool. We're going to break it down by first finding the pressure that's felt by the bottom of the pool. And that's given by rho GD. Now in this case, our units are in feet, which are the British units. So we're going to write that rho G is 62.5 pounds per cubic foot. In other words, we're using a weight density here. So when we replace that, we get 62.5 pounds per cubic foot. And the depth is 5 feet all across the bottom. So if we multiply those together, we get 312.5 pounds per square foot. Oops, I almost boxed that. That's not our answer. So a unit of feet cancels, and we just have square feet left on the bottom. Pounds per square foot, square feet. Now we can get the area of the bottom of the pool just by multiplying the dimensions on the bottom. 12 feet times 20 feet, which gives us 240 square feet. Then to get the force that's acting on the whole bottom of the pool, right? Pressure is just every little square foot, how much weight is there, how much force is there acting on that square foot. But the force we want is over the entire pool. How much force is acting on the entire bottom of the pool. So we just multiply these two numbers together. The number from the pressure and the number from area. And you end up getting 75,000 pounds. That's a lot of money. Just kidding. Pounds of force. Okay, so that's it for this video. Thank you for watching, and see you in the next video.